Chapter 7 IIR Filter Design. This chapter is about the design of IIR filters. After the end of the chapter, you should be able to determine the domain response characteristics of four types of low-pass analog filters in the S domain. Use BZT bilinear Z transform to convert the transfer function of domain S into Z. Pre-warp the frequency profile of the digital filter to obtain the design frequencies for the design of the analog filter. Now, IIR filters. Due to the peaked responses created by the poles, IIR filters can have sharper transitions between the passband and stopband of the same degree compared to FIR filters. The most common way to design IIR filters is to convert an existing analog filter design into a digital IIR filter. Okay, that's the main idea. Standard analog filters. Now, the four main types of analog filters are Butterworth, Chebyshev type 1 and 2, and elliptic. See figure 7.1. We'll just now refer to it and then come back to the lecture. Okay. Butterworth, Chebyshev type 1 and type 2, and elliptic. You see the differences. Butterworth, no repel in passband and stopband. Chebyshev type 1, repel in passband but without any repel in stopband. Chebyshev type 2, no repel in passband compared to the first one, but repels in stopband, and elliptic. Both passband and stopband contains repels. Okay. Now you see the amount of the repel in passband and in stopband. Okay. Now going back to the written parts. Butterworth has a uniformly decreasing amplitude response in both passband and stopband. Chebyshev type 1 has repels in the passband but no repels in the stopband, and Chebyshev type 2 has repels in the stopband but no repels in the passband. Elliptic filter has repel in both pass and stopbands as shown in figure. Now, the sharpness of the amplitude response in the transition region is the lowest for the Butterworth and the highest for the elliptic, because you just notice the payback. So it should have a benefit for elliptic. Very sharp transition region, but vice versa for Butterworth. If the two frequencies FP passband frequency and Fs stopband frequency are the same for all four types of filters, the degree of Butterworth will be the highest and the degree of the elliptic filter will be the lowest. Very important topic. Okay. Analog low-pass Butterworth transfer function. It is an all-pole approximation of the ideal state, and its transfer function is defined as follows. Apps to the power of 2 is equal to 1 over 1 plus omega over omega c, all to the power of 2n, where n is the filter degree and omega c is the cutoff angular frequency. It is said that the Butterworth low-pass filter has a maximally flat amplitude at zero frequency. Okay? Now amplitude to the power of 2, again repeating what we just showed you, is equal to h of j omega times h star of j omega conjugate, which is equal to h j omega times h minus j omega. So you can deduct Laplace transform. H of s times h of minus s will be equal to 1, 1. Okay, 1, 1 here, plus, just please notice, substituting s equals to j omega, so you will have s times minus s over omega c to the power of 2, just absorbing 2 here, and curly bracket to the power of n. Okay? So, with very simple mathematics, you'll reach to Laplace transform of Butterworth. Now, the roots of the polynomial of the denominator correspond to the poles of h of s times h of minus s and are located at the following points. S is equal to minus 1 to the power of 1 over 2n times j times omega c. Now, the amplitude of the poles will be omega c, and the phase is equal to pi times 2k plus 1 over 2n plus half pi, 90 degree. So, the last equation, the location of poles will be SP will be equal to omega c times e to the power of j pi 2k plus 1 over 2n plus pi over 2. What does it mean? It just shows a circle. You see here the radius and other information. We are just going to declare them. That is, there are 2n number of poles with equal angular distances and on a circle with a center at the origin and radius of omega c. Now, the n left poles of the vertical axis will belong to h of s, and the rest will be for h of minus s. Okay? Now, these poles are in the form of mixed conjugate pairs and are located on the left side of the S-plane. For example, a low-pass Butterworth filter with degrees from 1 up to 3 has the following transfer functions. N is equal to 1, so you will have h of s here is announced as Butterworth of s. B stands for Butterworth. You may use h of s, general name. Anyhow, b of s will be equal to 1 over s over omega c plus 1. Okay? N equal to b of s will be omega c to the power of 2 over s plus omega c times e to the power of j times pi over 4 multiplied by s plus omega c times e to the power of minus j pi over 4. Or simplified version, you see here, just please notice the pronunciation. Okay? 1 over s over omega c all to the power of 2 plus square root of 2, okay, times s over omega c, okay, plus 1, or what you see here. Both are the same. What about degree 3? I just want to leave it for you reading the same strategy. Now, what about figure? You see, the blue color shows the poles of H of S, while red is for H of minus S. So for degree n equal to 1, you will have a pole here, okay? What about n equals 2? Two poles, and n3, three poles, okay? Now, frequency response of Butterworth. You see here, it's a low pass filter. When the degree is increased to 2, you see the change in behavior of frequency response. And what about n equals to 3? Okay, so if you increase the degree of a filter, the transition region will be sharper. That's very simple rule. Oh, anyhow, the degree of Butterworth filter is computed or calculated in the following way. 1 minus delta p to the power of 2 will be equal to 1 over 1 plus omega p over omega c all to the power of 2n. And what about delta s? Here you see delta s for a stop band will be equal to 1 over 1 plus omega s over omega c to the power of 2n. Now, I will leave the next lines for you to read out them, leading to n being equal to ln of 1 minus 1 minus delta p to the power of 2 times delta s to the power of 2 over 1 minus delta p to the power of 2 times 1 minus delta s to the power of 2 divided by 2 ln of omega p over omega s. Okay. And then you'll choose the integer part. Example, 2.43 will be 3. It's sail, not floor. Okay? This sign in mathematics means sail, top integer from what you've got. So if you compute the degree, it cannot be a floating point number. It should be integer. Degree is 1, 2, 3, cannot be 2.43. Okay? Anyhow, the cutoff angular frequency is also computed as follows. Omega c will be equal to omega s over 1 minus delta s to the power of 2 over delta s to the power of 2 all to the power of 1 divided by 2n, or similar equation. Okay? For a low pass Butterworth, the amplitude at omega being equal to 0 will be 1, meaning pass. For delta p, passband frequency will be 1 minus delta p. For stopband frequency will be delta s. What about cutoff frequency? Always 1 over square root of 2 times maximum amplitude. Here it's 1, so times 1. Okay. Now example 7.1. Design an analog low-pass Butterworth for the following specification. Passband H frequency 2k Hz. Transition region delta F 800 Hz. Stopband attenuation 40 dB and passband ripple 0.1 dB. So now we are going to run a program inside Python environment. Okay, let's run the program. Here you see the location of the poles for the degree of 20. Okay, they reside on a circle with the origin at 0 and radius is equal to omega c. So you just here notice locations of poles. What about frequency response? It's a low pass filter, okay, 2000 and 800 delta F. Now we have computed cutoff and stop band color green and color red respectively. Now let's go back to the lecture note. What we have written here, you see the details. Okay, we use a definition estimate degree of Butterworth, just the equation you just saw. Similar idea. Now, another definition, compute angular cutoff for Butterworth. Okay. Find poles for Butterworth. Very simple mathematics. Okay. Find cutoff for low pass filter. How it's computed. Everything, every details have been shown here. What about a stop band? The same strategy. Now, declaration for the main program. 40 dB, 0.1 dB, delta F, passband frequency. No, stop band frequency for low pass will be FP plus delta F, and delta P and delta S are computed from what declared as dB. The next line is very simple and easy. Omega P, omega S. Now, finding the degree of the Butterworth, estimate degree, print it, and omega C and print it. Going back to the program, you see here the degree of the filter 20, and computed cutoff from equation will be a little bit different from what just declared. Of course, we declared passband frequency. Now cutoff is 2224. FC computed and FS computed. Everything we need have been provided for the researcher. Okay. The rest is simple, just showing the results and plotting them. Now, continuing our discussion. Take home. Use but order function to estimate the degree of the filter and compare the results with what you've got from your own function. Try the following command to compute num and denom and compare the new results with the previous ones. Using num and denom being equal to signal dot butter n degree omega c b type low, analog type true, because if you leave it as false, the program will assume that you are calling digital form. We haven't just declared it. Okay, later you'll get familiar with it. The next question, find the location of the zeros as well. Where are the zeros? We just show poles. What about the zeros? The next question, find and plot the phase response to and modify the program to show the poles of h of minus s, like in figure 7.3 in red color we showed it. Now we want you to add it inside your Python modified code. Do a research with modified parameters. Change APAS or any parameter declared inside the program. The computed value for cutoff frequency is equal to what we just mentioned, while one obtained from the frequency response is equal to somehow different. Okay? You see here the point 024 and here 124 and the rest. Why should they be different? In order to be able to have an answer, the solution is increase the resolution by changing the syntax from omega being equal to np dot linear space 0 comma 1.5 times omega s. This time 2000 samples will be changed into higher resolution. Okay, 10,000. Now the results will be the same. Okay, so here you see the role of resolution. Higher resolution, of course, it's better. Now try high pass, band pass, and band stop filters for Butterworth 2. It means you need to write the code.